Welcome to our explainer. Today we are diving deep into nanotechnology, a world so incredibly small it's almost impossible to picture, but one that holds both unbelievable promise and maybe some serious peril.
All right, let's just jump right in with a question that, might sound a little bit crazy. We all know what gold looks like, right? That classic, shiny, golden color. But what if I told you that's not always the case? Because when you get down to the nanoscale, gold is actually red. Yeah, red. You shrink a particle of gold that tiny and its properties change so much that it plays with light in a completely different way. This is the wild, fascinating world of nanotech, where all the familiar rules of physics kind of start to bend.
So, how is that even possible? Well, to get our heads around it, we first need to understand what nanoscale really means, and why being this small isn't just about size, it's about being fundamentally completely different.
Okay, so a nanometer is 1/1000th of a meter. It's hard to even imagine, but let's try. A single human hair, that's about 80,000 nanometers wide. So we're talking about a scale where we can literally manipulate matter, atom by individual atom. And this shift in scale has some mind-blowing consequences. Take graphite, for example. The soft gray stuff in your pencil. If you could take a single sheet of those carbon atoms, just one atom thick, and roll it up into a tiny tube, you get a carbon nanotube. It's the exact same element, but this new thing you just made is 100 times stronger than steel and has amazing elasticity. See? It's not just smaller, it's a whole new material.
So if we can create entirely new materials just by changing their shape at this scale, what can we actually do with them? Well, we can start to talk about the real building blocks of tomorrow's technology.
One of the most incredible building blocks is something called a quantum dot. These are semiconductor crystals so tiny that their behavior is totally run by the weird rules of quantum mechanics. We're way beyond just making things smaller here. This is a whole new kind of physics.
And here's where it gets really cool. The magic of these quantum dots is that their color is decided purely by their size. That's it. It's an effect called quantum confinement. So you can take the exact same material, and by just making the crystal a little bit bigger or a little bit smaller, you can make it glow red or green or blue. It's almost like you're programming light itself.
And this ability to program them has some absolutely staggering applications. In medicine, they can be used to tag and track individual cells inside the body. In your living room, they're already making TV screens brighter and way more energy efficient. And they could completely change everything from solar panels and lasers to the very future of quantum computing.
Our other main building block is that carbon nanotube we talked about. And remember, all it is a single one-atom thick sheet of graphite, just rolled up into a perfect, seamless tube. It's this simple, elegant design that gives it all of its incredible powers.
And they're not all the same either. You can have single-walled tubes or multi-walled ones, which are kind of like tubes inside of other tubes. But here's the really amazing part. Depending on the exact angle you roll up that sheet of graphite, a nanotube can either conduct electricity like a metal, or it can act like a semiconductor, which is, the foundation of all modern electronics. So when you put that insane strength and that unique conductivity together, you can build things that sound like science fiction. Look at this. These are actual nanotweezers. The arms are made of carbon nanotubes. By putting a voltage across them, scientists can literally open and close them to pick up something as small as a single molecule. I mean, this is engineering on a scale that's just hard to wrap your head around.
So the promise here is obviously enormous. But you know the old saying, with great power comes great responsibility. And that brings us to a really crucial pivot in our story. A bit of a cautionary tale.
History is just littered with technologies that were hailed as miracles at first. As researcher Mark Weisner from Rice University points out, things like CFCs and DDT, they were seen as revolutionary fixes for huge problems. But it was only much, much later that we discovered their absolutely devastating impact on the environment. So the question becomes, are we about to make the same exact mistake with nanotechnology?
And that forces us to ask a really tough question. Is it possible that the very properties that make nanomaterials so powerful, their tiny size, their high reactivity, their weird new behaviors, could also be the very things that make them a risk to us and our planet?
And these aren't just hypotheticals. Scientists are taking these concerns very seriously. For example, the long, thin shape of some carbon nanotubes looks disturbingly similar to asbestos fibers, which immediately raises red flags about lung damage. For a lot of these nanoparticles, we don't know the long-term effects. And there's the fear of a Trojan horse effect, that these tiny particles could grab onto other pollutants and carry them into our bodies or ecosystems where they otherwise couldn't go.
So, the potential is massive, but the risks are still kind of fuzzy. How do we move forward? Well, that brings us to the final and maybe most important part of our explainer. How do we innovate responsibly?
The key, it seems, is to learn from the mistakes of the past. This time around, instead of just releasing something new and waiting to see what bad things might happen, the goal is to build safety right into the process, from day one. It's all about being proactive instead of reactive.
And a really powerful tool they're using to do this is called control banding. It's a risk management strategy made for exactly this kind of situation. We've got a new substance, and you don't have all the safety data yet. The idea is actually pretty simple. You match the potential hazard and the potential for exposure to a specific level of safety controls.
And here's how it works, in 4 pretty logical steps. First, you gather every bit of information you can find. Second, you assess the potential hazard. Is it shaped like something dangerous? Is what it's made of toxic? Third, you figure out the chance of exposure. Is it a dust that can get in the air, or is it locked inside a solid? And finally, you combine those factors to decide on the right level of safety, everything from just needing good ventilation to needing full-on containment. It's basically a smart way to act safely, even when you don't have all the answers. So, as we wrap things up here, it's pretty clear that nanotechnology is about so much more than just making things smaller.
It's really about rebuilding our world from the atoms up, creating new materials with entirely new rules and capabilities. And the amazing thing is, this time, we have a real chance to build responsibility into the system from the very beginning.
Which leaves us all with the real challenge, right? It's not just a problem for scientists or engineers, it's a question for all of us. As we stand here on the edge of this incredible revolution, how do we make absolutely sure that tomorrow's miracles don't become tomorrow's mistakes?